Good day, everyone. Today we have a very interesting agenda. We will be learning how to do estimation when we receive the data sequentially. Indeed, what all the estimators that we have looked at until now have in common is that they use the entire data set. They cannot naturally operate on parts of it. That is why we say that they belong to the family of so-called batch algorithms, which are the ones that process all data at once and therefore cannot directly deal with data sets that grow in size over time. Of course, using the entire data set is beneficial in terms of estimation performance, such as, for instance, in terms of MSE, right? And the reason is obvious, right? If we have all the data at our disposal, we will not be doing worse than if we just have part of it, right? However, this comes along with important limitations, and one of them is delay. So we distinguish two components for the delay. One is what we call here data delay, which is a consequence of waiting until all the data is available. So this is especially problematic in many applications, right? Because it is often the case that data is received sequentially. Suppose, for example, that we are interested in estimating the reproduction number of a disease that is causing a pandemic. We are receiving new data every day, number of cases and so on. And with that, we need to provide an estimate of the reproduction number every day, right? So, of course, as the time goes by, we have collected more and more data, and our estimates would be of a higher quality. But what it wouldn't make sense is to wait until the pandemic is over and we have collected all the data to produce just the final estimate, let's say. Um, Even though that estimate would be of a very good quality because we would have a lot of data, it would arrive too late, okay? But waiting for all the data to be available is directly impossible in many other applications. So think, for example, in GPS sensors, such as the one integrated in our smartphones. These sensors are receiving signals from the satellites, and they need to use them to constantly estimate its location, right? So in principle, the satellites will not stop sending signals. So in this case, it's directly impossible just to collect all the data, right? And there are many other examples, right? So one classical example would be the one of recommender systems. So think, for example, that companies such as Netflix are constantly collecting information about the user's preferences, right? And with that, they estimate how much each user is going to like a given movie, right? So in this case, the data is not expected to and coming. So, these batch estimators are not, I mean, directly applicable in these situations. But there are many other examples. Another or the second component of the delay is processing delay. So if we wait too long, I mean, we would have collected, we will collect a great deal of data, and that may become, I mean, that may entail prohibitive computational complexity, right? So, and that holds even for the simplest estimators that we considered, such as the blue or least squares or LMMSE estimators, right? So, if the data set is too large, then we may need an exceedingly, I mean, too large number of arithmetic computations. Think, for example, in the LMMSE estimator, it involves the inversion of the covariance matrix of the data, right? So this matrix is number of samples by number of samples. So if we have 1 million samples, then that inversion is in practice impossible to compute. And it is not rare to have millions of samples, right? So, I mean, think, for instance, of an image, right? An image that has a few megapixels. That just one single image just has several millions of samples, right? So this is quite common nowadays. And another main limitation is also on data storage, right? So if we collect a lot of data and we are going to process it at once, then we need to store it somewhere, and that may take many terabytes perhaps, and that is problematic, especially in the case of embedded systems. To solve these limitations, we need to resort to the so-called online algorithms, which are those that process data as it becomes available. So the idea is to process the data that is available until each point in time, and to produce an estimate. And as more data is available, then we refine those estimates. So in the beginning, the estimates will be of poor quality in terms of estimation performance, measured, for instance, using MSE. But at least we have some estimates, and those estimates will become better and better as we collect more and more data. Therefore, such an approach has a much lower delay, right? Because we don't have to wait for all the data, right? And also because at every stage we will be processing a small amount of data. A truly online algorithm will also have a bounded computational complexity per update. So we cannot make an online algorithm by using a batch algorithm at every stage over the entire over the whole data until that point, right? We need something smarter that uses the past estimates and probably some additional information, but that is constant in size, right? To improve to come up with the next estimate. And they also a purely online algorithm will also discard past data, so we don't have to store the previous data. We just at each time step we just compute an estimate and perhaps some summary of the data, and then that is what we use in the next step together with the newly received data. In the first part of the lecture, we will see how to obtain LMMSE estimates in an online fashion. And in the second part of the lecture, we will apply those results to introduce the famous Kalman filter. So the key is to understand how one LMMSE estimate can be updated when more data is received. So to that end, suppose that we are interested in estimating a vector of parameters given two data vectors, but this one is available at time 1 and this one is made available in at time 2. Okay, for simplicity, let's assume that the means are 0. This entails no loss of generality, as we have already discussed. The problem can be formulated in this way. There are two steps. At time 1, we are given x1 and the moments, of course, and we need to find the LMMS estimator of theta given only x1. Okay, and in the second step we are given this previous estimate, right, together with the data x2 and of course the moments, and our goal will be to find this LMMSE estimator, okay, the one that uses all the data. So the first step is straightforward. We just need to apply the general expression for LMMSE estimators that we know very well at this point. Since the means are 0, we see that this simplifies. The second step is more tricky. So in what we see here is that we cannot directly apply the properties of LMMSE estimators that we know because these two vectors are not necessarily uncorrelated. Okay, if they were uncorrelated, we could apply the property of additivity over uncorrelated data, but this is not the case. So let's see how to deal with that. And this is when the interesting part comes. This is what I think it's the very, very smart trick. The idea is to subtract from this vector its LMMSE estimator given the first vector. Okay, and since the means are 0, this is a linear function of x1, and it can be easily seen that these two vectors and these two vectors are related by an invertible linear function. Therefore, these two LMMSE estimators are the same as per our the property that we saw last time, about the invariance to invertible functions of the data. Okay, so let's look closer into this term here. This is what we call the innovations. It captures the surprise, what x2 brings on the table that we didn't know just by looking at x1. So it's the new information. And to see what is the relation between this vector and this one here, let's look have a closer look at this estimator here. This one is the solution of this sub-problem here. Given x1, we need to find this LMMSE estimator. The data of this problem is therefore x1, and the error will be x2 minus the LMMSE estimate. Okay, and just by invoking our mantra that the data and the error are uncorrelated, we conclude that these two vectors, so this vector and this vector, are uncorrelated. Okay, and this is the key, this is the trick. Okay, what we call here the innovations trick. Now we can apply the property that we mentioned earlier about additivity over uncorrelated data and decompose this LMMSE estimator as the LMMSE estimator of theta given x1, okay, plus the LMMSE estimator of theta given this second vector here given the innovations. So we see that we managed to decompose this LMMSE estimator that in terms of the LMMSE estimator of the previous step, okay, plus this LMMSE estimator. So at this point we see that this will in general depend on still depend on x1, but we will see how to deal with this. Just for a notation, note that this will we use the subscript to denote the time up to which we use the data for computing this estimate. Okay. So now let's get a little bit more specific. In the previous slide, we assumed a generic joint distribution for the parameters and the data. Now we will be focusing on the special family of joint distributions determined by the so-called sequential Bayesian linear model. So this model is just the same as the conventional Bayesian linear model. The difference is that now we observe one sample at a time. We will be changing our notation. In the past we used square brackets to refer to the nth sample. Now we will be using a subscript, and this is just to make the expressions that are coming up more pleasant to our eyes. So we see here that this is the sample observed at time 1, this is at time 2, and so on. If we concatenate them, or we stack them together to form a data vector, then we will see that this is the same. This would correspond to stacking these vectors h, okay, that they would become rows of a matrix, which is precisely the matrix H from the Bayesian linear model. Note as well that the word Gaussian is not here for good reason. Again, the LMMSE estimator does not depend on the shape of the PDFs, it just depends on the first and second order moments, and therefore nothing is gained by assuming Gaussianity. The means will be assumed 0, as always, without loss of generality, and we will be given the moments of theta and the w's. Okay, and besides, we will be assuming that theta is correlated with all the noise samples, and all the noise samples are uncorrelated with each other. So the problem from the previous slide now becomes the following. In the first step, we are given x1 and h1, okay, and of course the moments, and we need to find the LMMSE estimate of theta given x1. And in the second step, we are given the LMMSE estimate from from step 1 together with the data at step 2 and H2, and the goal will be to find this LMMSE estimate. So this is not difficult. I suggest that you first try on your own, so we do not get bored with myself showing very long expressions. It's important to be doing these things, learning to do these things with a pen and a paper, and just looking at the slides makes it difficult to follow this lecture, I think. Okay, so this is the solution. This LMMSE estimator can be found just by using the general expression for LMMSE estimators that we know very well at this point. Now one can just use this first equation to write the estimate in this way, and what remains is to apply properties of variances and covariance, right? So here we apply this the property that this covariance will decompose as the sum of these two covariances. Note that this property holds even if even in the case where theta and W1 were not uncorrelated, right? But in this case here we are expressing this variance as the sum of these two variances. And remember that for applying this property we do need that theta and W1 are uncorrelated, but this is assumed here. Now we just use that theta and W1 are uncorrelated, and this expression just simplifies in this way. So this is what we have defined here as K1, right? It's a column vector that multiplies x1, so this concludes the proof. And to solve step 2, it will be very useful to first obtain the covariance of the error from step 1. Okay, so in this exercise the goal is to show that that covariance matrix is precisely given by this expression. Okay, so this covariance can be easily computed just by using the general expression for the covariance of an LMMSE estimator that we also know by heart. Now we just need to use this equation here, and again apply properties of the properties of the covariance and variance, which just results in this expression here. By taking a common factor to the right, C theta theta, and using this definition here, we arrive at the desired expression. So now we know not only the LMMSE estimator at step 1, but also the covariance matrix of its error. So let's go for the second step. As we said earlier, we will be relying on the notion of innovations, which remember is given by x2 minus its LMMSE estimate given x1. So let's obtain this estimate here. We just start by substituting here the definition of x2, okay, and now we can apply the additivity of LMMSE estimators that we saw in the previous lecture. to obtain this expression here. And now we just need to realize that W2 and X1 are uncorrelated, and therefore this LMMSE estimator equals the prior mean, or the mean of W2, which is 0. So why are they uncorrelated? Well, the reason is that X1 is a function of theta and W1, and both of them are uncorrelated with W2, right? And here we just apply, regarding this term, we just apply equivariance to linear functions of the parameters. So at this point, it is important to develop some intuition, because the expressions that we are going to see are sometimes complicated, and it is easy to make mistakes. So it is very important to look at those expressions and be able to assess whether they make sense or not. So let's start by this simple example. Here we have an estimate of theta 1 hat, and this multiplying it by H2 transpose gives us an estimate of X2. So we can see that this makes sense, and given the definition of X2. So to see that, imagine for a moment that we were requested to provide our best guess of X2, but we don't know theta and W2, okay? So in that case, the most natural guess is to replace each of these guys here with their means, okay? So this would be 0, and this would be 0, so our best guess for X2 would be 0, right? However, if we had some estimate of theta available, it would intuitively make a lot of sense to plug it here, right, and obtain X2 as H2 transpose times that estimate. And this is not something, this is not far-fetched, right? This is what people that don't know estimation theory unconsciously do, and we do ourselves. So imagine, for example, that we go to the grocery store and we take some, let's say, bananas, right? And we see on the label that the price of the bananas is like 2 euros per kilo. So what we do is more or less with our hand we estimate the weight of those bananas. Let's say our estimate is that they weigh half a kilo, let's say. And what we unconsciously do to estimate the price is to multiply that estimate with the price of the bananas per kilo, right? So half a kilo times 2 euros per kilo yields 1 euro, okay? So this is the same as we are doing here. This would be the weight of the bananas, or we would put here our estimate of the weight of the bananas, and this would be the price per kilo. So what I'm just trying to say is that this makes sense and agrees with intuition. So we will be recurrently using this term of best guess whenever we want to talk about intuition. That's just not to confuse it with the term estimator or estimate, which as we have seen, they have very precise mathematical meanings. We now substitute this LMMSE estimator here, okay, and this yields the innovations. So Now we are ready to apply the innovations trick, which remember that it states that this LMMSE estimate is equal to the LMMSE estimate given x1 and I2. So the information received at x1 and the new information that is obtained at step 2. And as we said earlier, these two quantities here are uncorrelated, and therefore we can apply the property of uncorrelation, additivity over uncorrelated data of the LMMSE estimator. So this one is just the estimate from step 1, and here we have just used the general expression for the LMMSE estimator. So what we need to do is to compute this covariance and this variance. Let's start by the variance, and I suggest that you try to show that it is given by this expression. The proof is very simple. Okay, this is the solution. The variance of I2 is therefore the variance of this guy here. Okay, now we just use the definition of x2, which is here, and take H2 transpose common factor. Okay, so this is the variance that we need to compute. The key here is to note that W2 and this vector are uncorrelated. And the reason is that on the one hand, theta and W2 are correlated by assumption, and on the other, theta 1 hat is a function of x1. It's a linear function of x1, and x1 depends on theta and W1 only, but both theta and W1 are uncorrelated with W2 by hypothesis, right? Therefore, we conclude that this vector and this vector are uncorrelated, and we can apply that the variance of the sum equals the sum of the variances here. Now, just by using the properties of the variance and the definitions in the previous slide, yields the desired expression for the variance of the innovations. So the next step is to obtain this covariance here. Again, I suggest that you try to show that it is given by this expression. Okay, so we start by using the expression for the innovations and the expression for, or the definition of x2 here. And this is what we obtain. Now we just take H2 transpose common factor and note that theta and W2 are uncorrelated. So this is what we obtain. Now, just as we know, this H2 transpose comes out without the transpose, and what we find here is something that looks pretty much like this. This R1 would be the covariance of theta minus theta 1 hat and theta minus theta 1 hat. So we miss here minus theta 1 hat in order to write it in this way. So let's see if we can add it somehow. To that end, let's look at this covariance here, and where this is the LMMSE estimator from the first step, which we showed that was given by this product here. And here what we just need to realize is that this was the data in step 1 and this was the error in step 1, and therefore since the data and the error are uncorrelated, this covariance is 0. This means that we can subtract it from this term here, and nothing will change, right? And now one can just apply the properties of the covariance to combine these two terms in this way. So note that we typically apply this property in the other direction, right? But obviously it holds in this way, okay? Now, just by plugging these expressions in this one, we obtain the LMMSE estimator at time 2, which we see here that it is given by the LMMSE estimator at time 1 plus this correction, right, which is a linear function of the innovations, of the information that is new, and it is scaled by this coefficient here. It as always, it is good to perform some sanity check just to just to convince ourselves that we didn't do it totally wrong. So, for example, we can think what happens if h2 is small and relative to sigma w squared. In that case, it means that our signal component is very weak. We have a lot of noise, right? So in that case, we see that this becomes negligible, and this quotient here between h2 and sigma w squared also becomes small. This means that the correction is small. That is, if we have the signal is weak at step 2, we barely correct what we our estimate from before. And we will use the notation k sub 2 for referring to this vector in analogy to what we did in step 1, right, where it is here, yes, where the LMMSE estimator was k1 times x1. So this is at this point, by just this notation, this is when we start smelling that the Kalman filter is coming. Okay, so as we saw in the previous slide, using the LMMSE estimator at step 2 is a function of the covariance of the error at step 1, this capital R sub 1. So if now we want to go to step 3, we need similarly the covariance of the error at step 2. And this is what we are going to compute in this slide. Then this is our error, and we will be using R2 to denote its covariance. So at this point, you may try to show that this covariance is given by the sum of these two terms. Okay, so I hope that you didn't get lost, because in this kind of tasks it is sometimes difficult to navigate through the equations if we don't have a clear direction. So it is useful to think where we are going, just not to move randomly and arrive at even more complicated expressions. So here we want to arrive at something that is the covariance of the the error at stage 1, right? And what we have here is something that depends on theta and theta 2 hat. So let's try to express things in terms of the error at step 1. So to that end, we start by substituting this estimate, the estimate at time 2, with the expression that we found in the previous line, right? So this brings us closer to writing things in terms of epsilon 1, because now we have here theta 1 hat, right? And those appear in the definition of epsilon 1, right? However, we still have here this x2, and here we don't really see anything related to x2. So let's get rid of it. To that end, we apply its definition. So this is given by H2 transpose theta plus W2. Okay, so now we are getting closer, because theta is also in the definition of epsilon 1. Okay. So we can start by grouping terms. This is directly epsilon 1, and here, taking common factor H2 transpose, we also get H2 transpose times epsilon 1, and this K2 goes here. Okay, and what remains is this minus K2 times W here. Okay, so now is when we need to realize that W2 and epsilon 1 are uncorrelated. Why is that? Okay, well, epsilon 1 is given by theta minus theta 1 hat, and theta is uncorrelated with W2, so everything is fine. And regarding theta 1 hat, this is what we said earlier. Theta 1 hat is a function of x1, and x1 is determined by theta and w1, which both are uncorrelated with w2. So always be careful with this. Otherwise, the expression that you arrive at is not true. So and also be careful when with the properties of the covariances. Don't be tempted to write here a minus sign, right? That should be totally discouraged by your retina. Okay, you don't. Otherwise, you could get covariance matrices that are that have negative eigenvalues, right? So that wouldn't make sense. And finally, just by applying the properties of the covariance, then we will arrive at this expression here. So now let us prove that this expression can be simplified in this way. Okay, so this one is a little tricky, not because of the math involved, which is very simple, but it is possible to start surfing in random directions. So let's see, we start with the expression here, okay, and now we expand this product, which yields these terms here, and we take common factor K2 to both sides, so these two terms can be combined. So here we see that all the characters in this movie, R1, H2, and K2, are the ones in this movie, but we have only this exception, is sigma and W2. So we need some equation that relates these quantities, and that is precisely the definition of K2 from the previous slide. So if we just substitute that definition here, this is what we obtain. Here we can cancel one of these terms in the denominator with this term in the numerator, and we can also take common factor r1 to the right, and note that this term and this term will cancel. So now is when we can apply again the definition of K2, but in the other direction, and this will yield the desired expression. So now that we have solved step 1 and step 2, we would need to solve also 3, 4, 5, and so on. But the same procedure that we used in step 2 can be inductively applied to all those steps. We would obtain exactly the same expressions, just with different indices or subscripts. Okay. So let us summarize the resulting LMMSE or sequential LMMSE estimation algorithm. So we start by this initialization. The reason for this is that if we set R0 and theta 0 hat in this way, the expressions that we found for in step 1 are the same as the expressions that we found in step 2 with just with different indices, right? So at every step we first need to obtain this vector of coefficients. Then we use it together with the data received at that step to correct the estimate from the previous step. Okay, and finally we obtain the covariance of the error at that step, because it will be used for the k in the next step. So note here that these definitions also make sense, right? Because Rn was the covariance of our error, and if we don't have any data before seeing any data, the covariance of the error is obviously C theta theta. This is the uncertainty a priori, right? And this the rest would be the uncertainty after seeing n data samples. And also this one makes sense as well, because this is the best the estimate of theta before seeing any data, which of course coincides with the mean a priori, which is 0. So another important observation is that this algorithm produces exactly the LMMSE estimator. So there is nothing that we lose in terms of estimation performance relative to obtaining the LMMSE estimator in batch form. And this is not something common in online algorithms. Typically, with online algorithms, there is some certain loss of performance and relative to their batch counterparts. And just a few additional remarks. Note that whenever the parameters and the data are jointly Gaussian, the LMMSE estimator coincides with the MMSE and the maximum a posteriori estimators. So this means that we have not only derived a an online LMMSE estimation algorithm, but we have also derived online versions of this algorithm for that situation, which is a relatively common assumption. And also note that the old data measurement vector coefficient correction coefficient vector and error covariance matrix can be thrown away after they are used. So here we see that each iteration depends on quantities that are from its own the same time, like hn, right, and xn. But it also depends on the on previous quantities rn minus 1, for instance, and theta hat n minus 1. However, it doesn't depend on anything older than that. So whatever is older can be just erased. We don't have to keep it. This is different from what we would need to do in the to obtain the LMMSE estimator in a batch fashion, right? So with this one, the memory will grow with time, and with this approach, the memory requirements are constant. So it's bounded memory complexity. And another interesting feature of this algorithm is that it assesses its own performance. So it not only gives us the estimates, but also the quality of those estimates, and there's no additional computation required. So it's just a byproduct of this iteration here, of the process to find the estimates. So as an exercise, I strongly recommend trying to generalize this algorithm to accommodate mini batches. So this is when at each time step we do not, we observe a vector of samples rather than just a scalar as we assumed until now. So therefore, this is like becomes a matrix rather than a vector, okay? And if you do it, then you will be in a very good shape to understand the Kalman filter, which is what is coming up.